Hello everyone, welcome to our video. I'm Madeline.
And I'm Akiho.
Today we will be your teachers.
We hope that you love chemistry as much as we do. So what exactly are we going to learn today?
In this lesson, we are going to study kinetics. Here is your learning objective.
The student is able to connect the half-life of a reaction to the rate constant of a first-order reaction and justify the use of this relation in terms of the reaction being a first-order reaction.
Let's get started.
Before we dive deep into this topic, let's go over a few key terms.
The area of chemistry that is concerned with the speeds of reactions is called kinetics. In kinetics, we study the rate at which a chemical process occurs.
What type of chemical processes?
Any reaction. The reaction mechanism is how the reaction occurs.
Wait, so what does the reaction mechanism have to do with kinetics?
The reaction mechanism will describe the order in which the bonds are broken and formed, as well as the change in the relative position of the atoms over the course of the reaction. It is important to know the steps of a reaction when determining the rate law.
The rate law is an equation that relates the reaction rate to the reactants, and sometimes even the products. We will talk about equations for rate laws coming up in the video.
One type of reaction is called a first-order reaction. A first-order reaction is one whose rate depends on the concentration of a single reactant raised to the first power.
You can pause the video here to take notes on these key terms if needed. What affects reaction rates? Temperature. Higher temperatures speed up reaction rates. Concentration. Greater concentrations have a faster reaction rate. A catalyst. Its presence speeds up reaction rates. Physical state. More homogeneous mixtures have a faster rate. So what are we learning about now?
First-order reactions.
What type of reaction?
First-order reactions. Here is the integrated rate law for first-order reactions.
Half-life is the time required for one half of the reactant to react. For first-order reactions, half-life is constant. For second-order reactions, half-life gets longer as the reaction proceeds. It is used as radioactive decay to measure age of objects. Here is an example of a half-life graph.
Though it is impossible to predict how long it will take for a particular atom to undergo radioactive decay, we can predict the average rate of decay for a large number of atoms. The half-life is the average amount of time it takes for half of the atoms of an isotope in a large sample to decay into a different isotope or element. Each isotope has its own characteristic half-life. Half-lives can range from billions of years to less than a second.
How can we model the half-life of an element like carbon? We can't wait 5,730 years for it to decay.
Here is a simple experiment that will model the half-life of an element. For this lab, you will need a shoebox, 100 M&Ms, a stopwatch, and we will be making a graph.
The M&Ms will represent atoms, since the M&Ms are double-sided. One side has an M on it, and the other is blank. M&Ms that are face up with the M showing will represent the decayed atoms.
We will start this experiment with 100 undecayed atoms. To start, place 100 M&Ms in the box. Shake the box for 5 seconds. After 5 seconds, open the box and remove the atoms that are face up. These are the decayed atoms. Leave the non-decayed atoms in the box and count how many are left. Record this on the table at 5 seconds. Keep shaking and removing the decayed atoms until all atoms have decayed. After 5 seconds, 46 atoms were decayed. You're going to record that. Continue this until all of your atoms have decayed.
Find the half-life of the reaction of butyl chloride with water. First find K, the rate constant. K will be the inverse slope of the line. Use 2 points to find the slope. Use the integrated rate law equation to find the half-life. Have the initial concentration equal 1 and the concentration at time t equal 0.5. T will represent the half-life. The half-life is 350 seconds.
Here is a review of the concepts we went over in this video. You can pause the video to take notes if necessary.